solid angle. Okay, then come to sensitivity. Sensitivity is how much capable of producing an usable signal for a given type of radiation and energy. It depends on detector properties, cross section for radiation interaction, detector noise, and it normally expressed in counts per exposure or charge per dose. And the last one is dead time. Dead time is the time duration for which detector remains insensitive to incoming radiation pulse. Mainly in GM counter, we can see that this dead time dominates, and it's around 100 to 300 microsecond. Means within that time, if another pulse will come, then the GM counter will remains blind for that particular pulse. So one detector should have some characteristics so that we can say that yes, it is useful to our particular like application or not. So for dosimetry purpose, that in our hospitals or in our daily to daily life, we use detectors for dosimetry purposes. So for that, it should have certain characteristics. So first one is it should have a minimal variation in sensitivity over a wide range of energies. Second, it should have a suitable volume to measure expected range of exposure. Like in absolute dosimetry, we use Farmer chamber. So Farmer chamber have a volume of 0.6 cc. So we should not use it like, or we are not using like 100 cc volume chamber, or for absolute dose measurement in or like 1 cc, 2 cc chamber, like that. So it should have a suitable volume to measure expected range of exposures. Then it should have direction independent, dose rate independent, minimum stem leakage, means it should have a very minimum stem leakage. Stem leakage means the leakage radiation other than the sensitive volume. Okay, so it should have a minimum stem leakage. It should have a minimum recombination loss. Means recombination loss means when radiation falls on a detector medium and ionization occur, just after ionization, if electrons and positively charged ion they got recombined, then we will have a loss in our output due to recombination. So detector should have a minimum recombination loss. Coming to the classification, detectors are classified mainly into these four categories. First one is gas field type detector, then scintillation detector, then solid state or semiconductor based detector, then some other types detector. So gas field detectors are again classified into these three, mainly these three types: ionization chamber, proportional counter, GM counter. Scintillation detectors are mainly of two types, like organic scintillator and inorganic scintillator. Solid state semiconductor detectors are mainly two types of detector that we use under this category, like silicon detector and germanium detector. And some other types detector like film detector that I told in our first few slides, that that radiographic film or radiochromic film detector, thermoluminescent detector, optical luminescent detector, and then chemical dosimeter. So starting with gas field detector. So what happened in this type of detector? See, this is my detector volume. So when ionizing radiation enters into the detection volume, it creates ionization, means positively charged ion and then electrons. So we applied the bias voltage like this. This is the bias voltage. When we applied the bias voltage, positively charged cathode and anode, this bias voltage effect creates an electric field inside this detector medium. In the influence of electric field, electrons move towards the anode and positively charged ions move towards the cathode, and we obtain a current in the outer circuit. Okay, so this is the basic principle of gas field detector. Whether it's the ionization chamber or the proportional counter or GM counter, it all works in the same principle, like formation of ion pairs, electrons and positively charged ions. So when we plot a characteristic curve for these gas field type of detector, we can obtain a graph like this. So in this graph, you can see certain regions. This one is the first region, which is known as recombination region. This one is the ion saturation. This one is proportional region. This one is limited proportional, and then Giger-Muller region. Another region is the discharge region. Okay, so in this case, what happened when the voltage voltage is very low, like near zero, the when radiation interact with the detector medium and creates electron and this positively charged ion, this voltage is not sufficient to move them apart. Okay, so they easily get recombined with each other. So the voltage pulse or the pulse amplitude is very low at this point of time. So our voltage is increasing gradually. So in this way, the recombination suppresses, and then ion saturation region comes. This ion saturation region, what happens, this ionization these ion pairs which are formed in the inside the detector, they all get collected in the outer device or in the anode. So what happened, the rate of formation of the ion pair is constant. So the amount of ion pair formed, they got already collected in the anode. So we see an ion saturation region. So voltage between this and this, we are increasing the voltage, but there is no increase in current in this region, because the amount of charge created, they are already collecting in my outer circuit. So it remains as a saturation region. Then come to the proportional region. In proportional region, what happens, when these electrons voltage increases, these electrons get sufficient energy, they drift towards the anode with a sufficient speed, and during that drifting, they ionize the gases in between, and due to that secondary ionization, the charge or the pulse amplitude increases linearly, or we can say that the output is proportional to the initial ion pair created. Okay, so you can see a linear increase in pulse amplitude during this region. So the term we use for this proportional region is gas multiplication. Okay, so main fundamental principle behind proportional region is gas multiplication. Then when we increase further the voltage, limited proportional region comes. These positively charged ions are also creating with electrons. Okay, and as they are heavy particles, they move very slowly towards the cathode. Due to that, they affect the external electric field. Okay, they create a cloud inside the chamber, and that suppress the external electric field. That's why we can see the pulse amplitude increases, but not in a linear fashion. Okay, it's a non-linear fashion. That's why it's called limited proportional region. Then if we increase the voltage further, a Giger-Muller region came where avalanche production is there. Means these electrons can ionize as well as excite the gas molecules, and during de-excitation of the gas molecules, they will release some UV photons, and that photons again contribute to formation of further avalanche. That's why here a very high pulse amplitude we can see. Okay, beyond this, if we work, then the detector damage will occur without any radiation also. There will be a presence of current in the output. Beyond GM region or beyond that discharge region, we can't operate the gas field detectors. So come to ionization chamber. Here the principle, I already explained the principle. So it's made up of an outer wall like this. This is an example of cylindrical type ionization chamber. This wall is normally made up of graphite or plastic or some air equivalent material. This is the anode, which are mainly made up of aluminum. This one is some guard electrode. This guard electrode normally create a space, or it like this separate the outer cathode and inner anode, and also it creates the sensitive volume, and it also helps to minimize the leakage current in the outer circuit. Okay, next, the field gas we use normally are like air, hydrogen, or some inert gases. Like in pressurized ionization chamber based survey meter, we use inert gases. Okay, but in our daily to daily, like absolute dosimetry ionization chambers, Farmer chamber or PP chamber, we use vented type, means the gas inside the chamber is air. Okay, so this is again the saturation region explanation. So 100% initial ions are collected. The rate of formation of ions remains fixed, and as much as ions are getting produced, we are collecting all of this. So 100% initial ions are collected. So we obtain a saturation region. So commonly used ionization chambers in radiotherapy are this thimble chamber. It's a skeletal diagram of thimble chamber. Then parallel plate chamber. Here, this one is the cathode and this one is the anode, and these two are the guard electrode. This is a spherical chamber. Means in our daily to daily practice, we are not using this spherical type of chamber. Okay, these spherical type of chamber are designed in order to make the chambers direction independent. Okay, like for parallel plate chamber, it has a entrance window. Okay, we can't when we measure in gantry 0 degree, we can measure it. But if we switch to gantry 0 degree to gantry 90 degree, then we need to flip that chamber towards the entrance of the beam. Okay, but in case of spherical chamber, as it's a spherical shape, we can irradiate it uniformly. Okay, again, this one is a example of well type ionization chamber. So types of ionization chamber and its use. This is basically I took from Khan book. It explained very well the principle of thimble chamber. So what happened in thimble chamber? We know in order to for proper dosimetry, we need to have a charged particle equilibrium. We must have charged particle. Hello. Yes, sir.
Hello.
Yes. Hello.
Yes,
Hello,
ma'am. Now you're
Arunji.
audible, actually. Yes, ma'am. Now you're audible.
Oh, sorry. Actually, some power fluctuations in our department. That's why.
It's
Okay.
okay, ma'am. Yeah.
Hello.
You can continue. Yeah.
Okay. Sorry. So, coming to the types of ionization chamber and its use. Yes, I am telling about this. Yes, this is air cavity and surrounding it's a air cell. Okay. So, in this case, what happened? For CPE to exist, we know that the amount of electron produced within the volume, it must deposit its energy outside the volume, and similarly, the electron generated outside the volume, it must deposit energy inside the air cavity. And the okay, so the distance between the outer cell and inner cell such that it is in between the range of electron energy. Okay, so when we replace this air cell, we can't this is an hypothetical case, we can't make this air cavity and surround it with air cell. So we replacing this air cell with a solid air cell, means solid air equivalent material, we can make a thimble chamber. Okay, so this is a thimble chamber. So when we go for air, the in electron, we know in case of electron in air, the range is very greater. But when we move to solid, when we create a solid air equivalent cell, then it will be easier for us to achieve charge particle equilibrium with a very small distance. So you can see that in case of this farmer type chamber, the thickness is around 0.75 centimeter, 0.75 or 0.75 mm, like thing that. Okay, so it's very thin. As density get increased due to this solid replacement, we can achieve the CPE with very thin thin cell, thin air cell. Okay, thin air, solid air equivalent cell. So this is the basic principle of thimble chamber. And there are mainly two categories of thimble chamber. One is condenser type, which get obsoleted nowadays. So this condenser type chambers are the type of thimble chamber which can able to store the we can charge it just like power banks. No, we use power banks for charging, and then we can take the charge for to charge our mobile when necessary. That's similarly condenser type chambers are those specific type of chambers that initially we need to charge that chamber, and after that we need to keep it inside the radiation zone, and then when radiation falls into it, it creates electron and positively charged ion, and after irradiation we need to take it out from the like linac room and then measure it with some specially designed electrometers. Okay, so here like in our normal farmer chamber, we have a cable. Okay, so we normally we connect the chamber with cable and then with electrometer to measure the like active measuring we are doing. But in case of condenser chamber, it's a passive measuring. So in condenser chamber, the main issue was the greater stem leakage and then passive measuring. Then in order to overcome that, farmer chamber came, and we are very much well known to this farmer chamber as we are using in our daily to daily practice. This is the pencil ion chamber, which normally we use in case of CT dosimetry, like for this CTDI measurement. Okay, for that we use this pencil type ionization chamber, and this one is a pressurized survey meter based ionization chamber. This one is well type ionization chamber that we use in brachytherapy dosimetry and also in nuclear medicine for activity measurement, activity of radioisotopes activity measurement. This is an Octavius Phantom by PTW. Here also we are using parallel plate ionization chambers to measure the like patient specific QA. We are using this Phantom. Okay, but this one is is an example of a parallel plate ionization chamber, and this one is a extrapolation chamber. So with cylindrical chamber, it is difficult for us to measure the surface dose. So to overcome that, this extrapolation chamber and parallel plate chamber came. With extrapolation chamber, there are micrometer screws. With micrometer screws, we can adjust the the electrode spacing, that outer electrode and inner electrode spacing, and with the extrapolation we can measure the surface dose with this. So this is all about ionization chamber. Coming to the proportional counter. So for proportional counter, it operates higher voltage than ionization chamber. What happens when radiation come and interact with the gas medium? It creates a primary electron. This primary electron can drift towards the positively charged ion. During its drifting process, it further creates ionization. You can see here. Okay. So similarly, the ionization spans over the anode wire. Okay, so in this case, the electric field is very much important. So if the electric field is higher, then the probability of getting gas multiplication will be higher. So this higher electric field can be achieved with the help of a cylindrical geometry, and again with the help of this equation. In this equation, this is the electric field that is near to this anode wire. V is the voltage, applied voltage we are applying. R is the radius of this anode. B by A is the cathode inner radius, and A is the anode wire radius. Okay, R is the distance from this anode surface. Okay, so distance from anode surface. When this anode wire radius gets lower, then this electric field gets higher. Hello.
Yes, ma'am.
Hello. Am I
Yeah.
am I audible, Orange?
Yes, yes.
Yeah, you're audible.
Okay, so this type of higher electric field can be obtained with the help of this cylindrical type of geometry. So types of proportional counter, mainly I included the seal type and gas flow type, as we are not so frequently using proportional type of counters in our radiotherapy practices. So these proportional counters are mainly used for neutron surveys during in our LINAC, we have energies greater than 10 MV, and we know that when the energies exceeds 10 MV, then there is a chance of production of neutrons. So during commissioning, normally the engineer peoples, they bring this RAM counter with them, and the RAM counter is a kind of proportional counter which we use to measure the neutron dose surrounding our bunker. Okay, so main functions are neutron survey instrument, neutron spectroscopy, and alpha beta discrimination. So in proportional counter, we must have a field gas inside the proportional counter, not like AR in case of ionization chamber. So the gas must have a low electron attachment coefficient. As we are seeing, these electrons are the main producers for this gas multiplication. It should have a low electron attachment capability. This field gas, it should be pure. Noble gases are normally used. With field gas, quench gas are also being used. So in proportional counter, there is a chance of production of UV photon due to excitation of these gas molecules. When this electron comes, they can excite the gas molecule, and when the gas molecule get de-excite, they produce UV photon. That UV photon may create avalanche again. So in order to prevent that, we add quench gases in proportional counter. So come to GM counter. So again, GM counter operates in a high voltage than the proportional counter. Here, see, I told the UV photon, no, this UV photon is contributing to the avalanche formation. Okay, it can, like here one electron goes to the cathode, and in cathode another avalanche produced. So throughout the volume, we can see the avalanche production. Okay, so in GM counter, what happened? The true identification or true energy information get lost. Whether it's a small signal or a large signal, we can get a same amplitude for each type of radiation. So we can't distinguish between which type of radiation is interacting with the detector. Okay, so the energy information get lost in the GM counter region. So and there is no proportionality relationship, just like proportional counter, no proportional relationship between energy of incident radiation and number of ionization detected. A level pulse height occurs throughout the entire voltage, one same level of pulse. Okay, next, here also quenching is important. Why? Because with as electrons are producing, similarly these positively charged ions are also getting produced, and their mobility is very small. When they positively charged ion, they are going towards the cathode. When they interact with the cathode material, then they want to take electrons from cathode and neutralize themselves. During neutralization, when some energy release, and that energy if greater than the cathode work fraction, then electron can release from the cathode surface and contribute to the avalanche. Okay, so we should prevent that one. Okay, so in order to prevent that one, quenching gases are used. So mainly two types of quenching we are using in a GM counter. Either it's a external quenching or internal quenching. For external quenching, we need to keep the voltage down. Like the applied voltage, we can keep it lower the applied voltage. Or in internal quenching, we need to apply, or we need to keep some quench gas inside the detector, so that when the positively charged ion are moving towards the cathode, they transfer their energy to that quench gas, and instead of positively charged ion, that quench gas will move towards the cathode, and when it get neutralized with the cathode, the amount of energy released, they will utilized in dissociating that quench gas atom or molecules. So it will try to dissociate it, and it will not create any further avalanche in the detector. So these are some applications of detector. We use GM based survey meter, GM based contamination monitor, GM based counting setup. This is a GM tube. Okay, here we placed a detector. This is a teledetector, means telescopic detector. Telescopic detector. So here GM detectors are using. Here area gamma monitor in telecobalt room, in brachytherapy room, where active sources are present. There we need to place a area gamma monitor in order to see the dose due to this, in order to check the presence of radiation inside the vault. So coming to the scintillation detector, yes, I already explained that scintillation is a process in which a visible light will appear in the process. So if the visible light appears within 10 to the power minus 8 seconds, then we call it as fluorescence, and if the light is delayed, then we call it phosphorescence. See, in this case, A0 to A1 is energy state. Okay, so when it moves to this and this, it will take time. So this can be of what? Delayed fluorescence or phosphorescence. But if quickly emit the light, then we can call it as fluorescence. So scintillation detectors are again of organic and inorganic type. The ideal properties of a scintillators are, it should convert kinetic energy of charged particle into detectable light. Conversion should be linear, means light yield should be proportional to the deposited energy over a wide range. The medium should be transparent to wavelength of its own emission for good light collection. If medium will be opaque, then it can't be transfer the amount of light through itself, and then in output we can't see the like in output we can see the underestimate of the what incoming radiations interactions. Then decay time of induced luminescence should be short. Fast signal can be recorded. It should have a good optical quality, and refractive index should be near to glass. As scintillation detectors need to be mounted with photomultiplier tubes, and photomultiplier tubes are normally the front window of photomultiplier tube are made up of glass, so it should have a refractive index near to glass. So in organic scintillator, so here see, radiation interact with the electrons and it jumps to the higher energy state, and when it comes, so quickly coming is fluorescence. When it comes to this part and then comes, it will take some time, and this one is phosphorescence. Okay, so organic scintillators are mainly of three types, like pure organic crystals, mainly anthracene and stilbene are two types of scintillator detectors, which are pure organic crystals, and the advantage are they are they have highest scintillation efficiency, and limitations are they are fragile, difficult to obtain in large size, and directional dependent. Then come to the liquid organic solution. Normally in liquid organic, as it's a liquid, there should be a solvent like water or some organic solvent, then a scintillator, okay, then wavelength shifter. Okay, these wavelength shifter mainly shift the wavelength to the visible light section, so that our PMT can obtain the signal. Advantages are obtaining large volume resistant to radiation damage and high dose range. Limitation, dissolved oxygen acts as a strong quenching agent. Okay, quenching agent means it can take the the scintillation light, it can absorb these oxygens can absorb within itself. Plastic scintillator, organic scintillator dissolved in a solution when polymerized forms a plastic scintillator. Advantages are available in customized size like rod, cylinder, flat sheet, and inexpensive. Limitation, self-absorption of scintillation light. Coming to inorganic scintillator. So in inorganic scintillator type, what is the principle? Like there is a valency band and conduction band. When radiation falls in the detector, electrons shift from valency band to conduction band and then move to within the conduction band. Then it falls in an activator site. These activators are added in the detector in order to create this like these activators are created energy levels within this conduction band and valency band. So the light initially when valency band to conduction band and electron jump and eventually it will come down, it will emit a light which is not in the visible range or which we can't detect. But when we put some activator or when we incorporate some activator within the detector, then it will this conduction band will fall on this activator side, one of the excited activator side, and when it comes to the ground state of the activator side, it will release a light that we can see in our output. Okay, so mainly the types of inorganic scintillator we are using are alkali halides that are sodium iodide thallium activated, cesium iodide thallium activated, lithium iodide europium doped. Then slow organics like BGO, bismuth, germanate, ZNS AG means zinc sulfide, silver activated. These detectors are mainly used for alpha spectroscopy or alpha counting. Inactivated fast inorganic like barium fluoride, glass scintillator like cerium activated lithium. So in our department, like in radiation oncology department or in nuclear medicine or in radiology, we use this sodium iodide detector like in mainly in nuclear medicine. Okay, so the output of the scintillation detector, it will fall on the this photomultiplier tube. So what happened, see here gamma ray interact with the detector medium, it forms an electron, forms an scintillation light. This scintillation event creates a scintillation light. This scintillation light falls on a photocathode. This one is the photocathode. When it falls on the photocathode, it generates electrons, just like photoelectric effect. These electrons comes to this place. These are the dinodes. This is a structure of PMT. So when electron falls in this, it multiplied the electron, generate more electrons in the stage, subsequently create a pool of electrons with a single scintillation light. So PMTs are essential in order to when we are working with scintillation detector, PMTs need to be incorporated with the detector in order to get a usable or detectable signal, as it amplifies the scintillation light to a detectable signal. So these are some certain uses or applications of scintillation detector. See, it's a thyroid optic probe. Here, this is the probe where scintillation detector used sodium iodide thallium activated detector. This is a gamma camera. Okay, these two are the scintillation detectors. And here it's a PET detector. We know PET stands for positron emission tomography. So during when patient undergone for this positron emission tomography, two gamma photon will produce, and to see that gamma photon we use scintillation type of detectors. Then come to semiconductor type of detector. Here what happened, radiation enters into the sensitive volume. These like semiconductors are made up of p type and n type. When p type semiconductor, n type semiconductor, they come closer, they form a depletion region. This is the depletion region. So this depletion region is my sensitive volume for semiconductor type of detector. So radiation enters into the sensitive volume means radiation falls in the depletion region. In this depletion region, electron hole pairs will produce, and then electric field separates these electron hole pairs, and collected charges will produce the detectable current pulse. Here you can see that this is reverse bias. So these semiconductor detectors we always use in reverse bias condition. This reverse bias condition not only increase the depletion region depth or width of the depletion region, but also it minimizes the leakage current within the detector medium. Okay. Next, in our radiation department or radiation therapy, we have a silicon type of detector. See, this PTW silicon detector. Okay, types mainly silicon type, germanium type. So here for silicon detector, we know that during measurement, we don't provide any bias voltage to this type of detector. So it don't need any bias. Okay, like just ionization chamber. In case of ionization chamber, we are providing 300 volt for to obtain charge. Okay. Similarly, for PP chamber, we are providing 300 volt or 400 volt to obtain charge. But in semiconductor diode detector, silicon type, we don't provide any kind of bias voltage. So why it's don't need no need of providing any bias voltage? Here is the principle. So in depletion region, there is a potential difference. Okay, there is a potential difference exists, like in P type it's negative and in N type it's positive. So in this region, when radiation falls, it this radiation deposits its energy within this depletion region and it creates electron. This potential difference will help to move these electrons from one side to another side. Just after that, we can see a current in the electrometer without any applying of any voltage. This acts simply as a photo cell, like a solar cell. No, the so how the solar cell works. Similarly, this diode works. Hello, am I audible?
Yes, ma'am, you're audible.
Hello.
You can continue. Yeah.
Okay, okay. So this is how it works. It works similar to like photo cell we are using in the solar cells. So these are some uses of semiconductor diode detector. So mainly in radiology experiment or in X-rays or CT quality assurance test, we can use semiconductor detector. This is a Cobia Smart RF. RF means R for radiology, F for fluoroscopy. We use this instrument to measure the KVP, MS, linearity, then output voltage. So in these detectors, silicon detectors are used. Similarly, here one of our student performing the leakage radiation measurement with this scatter probe. This scatter probe is also a silicon type of detector, and this is the X-ray tube. So we are measuring the leakage radiation coming from the tube. This is the Nomex multimeter from PTW. It's also used for radiological experiment, in radiology department, like X-rays and CT. Similarly, this Piranha type of detector is a special type of silicon detector that is used in measuring this KBP and MS linearity, etc. in CT machine. And this is our machine, Linac machine, where this EPID, electronic portal imaging device, this EPID is made up of amorphous silicon detector. So yes, here also we are using semiconductor type of diode detectors. And this is a setup in our department, where this one is the HPG, high purity germanium detector unit. So here it need cooling, frequent cooling, or liquid in liquid nitrogen. So we place it, this divar, it contains the liquid nitrogen, which provides continuous cooling to the detector. So we obtain very low noise level with this type of arrangement. So coming to the radiographic and radiochromic film that I told. So the basic principle of radiographic film is silver halide crystal in the film forming a latent image. Latent image means a hidden image. After chemical processing, you can see the image. Radiochromic film polymerization in the film, permanent change in optical density. So here the principle is polymerization. Okay, so they are made up of some certain kind of chemicals that get polymerized after irradiation. Okay, so processing, it requires chemical processing, and here no chemical processing is required. Radiation response, image density increases with the dose. Response is strongly affected by processing conditions. Means like we need to use developer solution, then fixer solution, then washer solution in order to get the image. So during that processing also, the radiation response can vary for that film. Then optical density change in related to absorbed radiation dose and is generally more stable. Here in radiochromic, with radiochromic film, the optical density change normally occurs, and this is more stable as compared to radiographic film. Light sensitivity, yes, this is sensitive to visible light. It's also sensitive to visible light, but less as compared to radiographic film. And then means we can handle it in room temperature, room conditions, like room light and all. Okay, so reusability, it's not reusable, and radiochromic films are also not reusable. Main application: conventional radiography and historical radiation measurement, quality control. Here radiotherapy, dosimetry for spoke test, field size test, congruence test, etc. Then coming to thermoluminescent dosimeter, here what happened? See, in normally TL phosphor or OSL phosphor, we can see this luminescent kind of thing. So what happened? There is a conduction band and there is a valency band. When radiation fall, see, ionizing event by radiation. So one electron move from conduction band to valency band. Okay, and it travels through the valency band and falls one of the trapping center. These are the electrons trapping center, and these are the hole trap center. When electron lifted from conduction band to valency band, in order to fill this vacant place, a hole or a electron from this luminescent came and it rest here. Okay, so at a time in conduction band there will be no vacant. Okay, no holes, all are electrons. So from this hole center or this trapping center, electrons will come and fill the conduction band. But the electron which get lifted in the valency band, they move throughout the valency band, and eventually it will fall into the this electron trapping center. Okay, and it will stay there. When we provide heat or light, heat means thermally we need to stimulate it. When we provide thermal stimulation, it will release from this and again will go to the valency band and then move in the valency band and then fall in the hole trap. When it falls in the hole trap, it releases energy. Okay, light photon, which we can obtain or which we can read with the help of a TL reader. So in TL reader, we have a PMT which can see this light and again convert it into detectable signal. So this is the glow curve which we can obtain with this type of TL readout device. So glow curve is normally a graphical representation of the luminescence intensity emitted by the material as a function of temperature or stimulation time. It is obtained by heating a TL material and measuring the resulting luminescence. The glow curve typically exhibits one or more peaks. See, here is a peak and another here is a peak, but this one is more useful. Okay, this one is due to shallow depth. Okay, this one is due to deeper depth. Okay, each representing a specific type of luminescent center within the material. This is a shallow luminescent center and this one is a deeper luminescent center. Okay. Next, TLD batch reader. So we know in our daily to daily practice, we all wear a TLD batch. So it's look like this way. This is how a TLD batch look like. It has mainly three discs, three calcium sulfate dysprosium TLD discs. So mainly it is within that like cassette, and we have to wear it in our chest level, and after 3 months we need to replace it and check the radiation dose. So this type of arrangement or this type of TLD batch can be read out with the help of a TLD batch reader. So the circuit diagram looks like this. So here are the compartment where we can load this type of TLD batches. So at a time we can we can read up to 50 TLDs. We can place it in this. There are compartments for placing this type of TLDs, and it will automatically take one of the TLDs and then move to this place. Here, see, here PMT is there, and the heating effect is occur due heating effect occur with the help of this this nitrogen heating. Okay, so nitrogen gas flow heating method is normally used in this TLD type of badge reader, and it will heat the TLD phosphor, and the light will emit, and that will be detected by the PMT, and subsequently it will come to in the display that this much radiation dose obtained from this particular disk, then this particular disk, then this particular disk. Okay, so these are mainly portable and widely used for personal monitoring, reusable and cheap. uh, Dose range is 10 microgray to 10 gray, can measure high energy X-rays, gamma ray, and both high and low energy beta radiation, and fading occurs when exposed to high temperature. Then optical, see, in case of TLD, no, these are reusable, means we need to anneal these TLDs before reusing. Annealing means we need to keep these TLDs inside a hot air oven, inside which it get receive a high temperature, so that all stored information get lost, so we can use it freshly. So okay, so annealing is necessary here. Annealing done by making it irradiated with a high temperature. Okay, then optically luminescent dosimeter, these are the OSLs. Okay, similar principle, just like TL, but here the stimulation light is optical, means by means of laser or by means of LEDs we need to stimulate the OSLD. And here also some PMTs are there. Filters are necessary in both TLD and OSLD in order to cut the, like, if filter will not be there, then there will be some chance that this stimulation light can also this stimulation light can contribute to our PMT signal. So filters are there to cut this stimulation light or any extra light from surroundings. So this way it will work. And mainly there are three types of stimulation procedure. First one is linearly modulated stimulation. Here the stimulation light gradually increases from 0 to a particular level. Okay, and then continuous stimulation, sorry, this one is continuous wave stimulation, and this one is linear modulated stimulation. Okay, this the like this caption I have interchanged. Okay, so this one is continuous wave stimulation, means here the stimulation light intensity should be fixed. So if we set a higher intensity, then it will initially it will it will release all the trapped electron. In linearly modulated, like this one, no, this one linearly modulated, initially we set it at 0 stimulation light, then gradually we increase the intensity of stimulation light, and then eventually the trapped electrons get released from the this OSL. Okay, so this one is linearly modulated stimulation, and this one is continuously wave stimulation. Okay, I have by mistakenly interchanged these captions. Okay, and this one is pulsed stimulation. Pulse stimulation means the stimulation light we provide in pulse form. Okay, then just like TLD, these are also portable and commercially not so available, reusable but expensive. We can reuse it with the help of annealing. Here we sorry, this is not annealing, we say it as bleaching of optical luminescent dosimeter. Just like in TLD we say annealing, this one is bleaching, means we keep the detector here and provide it a high intense blue light so that all trapped electrons get released and we can reuse the detector freshly. Okay, dose range is 10 microsievert to 10 sievert. It can measure high energy X-ray, gamma ray, and both high and low energy beta radiation. Fading occurs when high intensity of light. Just like in TLD, when exposed to high temperature, fading will occur. But here, when exposed to high light, then fading will occur. Then come to chemical dosimeter. In our department, we normally prepare this pre-K solution and FBX solution. These are a kind of chemical dosimeter, and we used to irradiate these solutions with gamma radiation. So in case of pre-K solution, these pre-K solution are made up of mainly ferrous ammonium sulfate, then sulfuric acid, sodium chloride, and water. So when radiation interact with the solution, ferrous ion Fe2 plus ion get converted to Fe3 plus ion. Later on, with the help of this UV visible spectrophotometer, we measure the amount of or the absorbance that we are obtaining from ferric ion. So the amount of ferric ion produced, it means directly proportional to the amount of dose received by the dosimeter. Similarly, this is FBX solution. Here, xylenol orange we add. FBX, X stand for xylenol orange, B for benzoic acid, F for ferrous ammonium sulfate. So due to xylenol orange, the color looks like orange. Okay, so other chemical dosimeters are seric serous dosimeter, alanine dosimeter. They are very like this pre-K solution. It used very frequently in primary dosimeter calibration laboratories. And these dosimeters, like these chemical dosimeter, have a high dose range. Okay, like for pre-K solution, we can measure 40 gray to 400 gray. In FBX solution, we can measure 0.2 gray to 20 gray. Okay, so it has a higher dose range. So at last, to summarize this topic, I want to compare the chambers that I have discussed today, its application, advantage, and limitation. So first one is ion chamber. We are very frequently using ion chamber in our daily practice. So it has the applications are like absolute and reference dosimetry in radiation survey meter, in like measurement of like in 2D array or 3D array for this patient specific QA. Also we are using ionization chamber, brachytherapy, quality assurance, nuclear medicine, radiation like radioisotope activity detection. For that one also we are using ionization chamber. Advantages are based understood negligibly energy and angular dependency and size limitation. Okay, there are some angular dependency, like for parallel plate chamber there is some angular dependency, no, and size limitation, it has a limitation in size. Proportional counter mainly used in neutron survey and alpha beta radiation discrimination. Advantages are energy discrimination and higher sensitivity. Limitation, high and controlled operating voltage, frequent gas change we need to like encounter with frequent gas change problem in proportional counter. Similarly, GM counter mainly used in area gamma monitor and survey meters or counting systems. It has a greater sensitivity than ion chamber and proportional counter. It has issue of dead time, requires high operating voltage and quench gases. Similarly, scintillation detector mainly used in gamma spectroscopy, counting in nuclear medicines. And advantages are energy and radioisotope identification, and limitations are hygroscopic and costly. Diode detectors are mainly used in dosimetry, radiation survey. No bias requirement, radiation damage can easily occur for these diode detectors. Film, 2D dosimetry, profile, field size measurement, spoke test. For those things, we can use film detector. And advantage, small, lightweight, and used in machine QA. and it's not reusable. Similarly, luminescent dosimeter, personal monitoring, surface dose measurement, reusable, suitable for personal monitoring, its advantage and limitations are temperature and light sensitive fading occurs. Okay. Chemical dosimeter, absolute dosimetry may use we use in absolute dosimetry, and advantage high radiation dose, so we can use for like industrial purpose. When we want to do the dosimetry, we can use chemical dosimeter. And then limitations are passive reading, require chemical preparation, means each time you need to prepare the chemical solution for readout for in order to carry out the dosimetry. Each time you need to prepare the chemical dosimeter, prepare the solution, and then after irradiation also it requires time for readout. Okay, so you need to read you can read the chemical solution after irradiation with the help of UV visible spectrophotometer. Okay, so these are my references. You can go through this. I took this Nomex multimeter from PTW site, and also detectors for ionizing radiation, including course of practice. This one also from PTW site. Then I normally used to teach to my students from this radiation detector and measurement by Knoll, and then this FM Khan, and then from the Leo book. Thank you.